Okay, so looking at test 1 for PHYS1001, I'm going to go through and do some solutions. I'm going to try and do it as though I was in the test situation. So what I'm not going to do is explain in great detail how to do them. Okay, that's not what this is about. This is about, hey, how should I approach this in a test situation? And I don't guarantee I'll do a very good job. Please don't complain if it's not good. So let's have a look. So we've got, I'll start with question 1. We'll just work our way through. So we've got a steel, and we've got the linear coefficient of expansion, thermal expansion there. Rod has a diameter of 3 centimeters, and a brass ring with its coefficient of thermal expansion has an interior diameter of 3.005 degrees when both are at 250 degrees Celsius. What is the lowest common temperature at which the ring will fit onto the rod? So you can see that our initial situation is we have the rod there and we have the ring here. So there's our ring, here's our rod, and there's a little bit of a gap there. And so as we cool them down, the brass ring will contract faster than the steel rod. So you would imagine at some point that maybe there will be a very snug fit, and then below that temperature you won't be able to get the ring over the rod. Might not happen. It might be that that temperature is below absolute zero, so we don't know. We just better try and write some equations and see. So there's a ring, and the coefficient of linear expansion will give us the expansion around the ring, and that gives us the circumference, but the radius is proportional to that. So therefore the radius, the change in radius, is equal to alpha delta t times the original radius. Okay, and so the final radius of the ring is going to be equal to the initial radius minus alpha delta t r, which is the initial radius times 1 minus alpha delta t. And the same is going to be true for the cross-section of the rod. So we need, is there a temperature where these two will be equal? So we want 3 centimeters times 1 minus alpha steel delta t is equal to 3.005 times 1 minus alpha brass delta t, and we need to do some rearranging, and let's see if we can do that. Okay, thinking, brain's not working, not warmed up yet. So 3 minus 3 alpha steel delta t equals 3.005 times 1 minus alpha brass delta t. Well, 3, let's put 3 minus times 3.005. And what we're going to end up with by a bit of rearranging, if we add this, now we'll take that over there, so we get 3.005 alpha brass delta t minus 3 alpha steel delta T is equal to 3.005 minus 3, which is equal to 0.005. So, okay. So therefore, delta T times 3.005 alpha brass, 3 alpha steel, is equal to 0.005. So delta T equals, okay, calculator on, 3.005 times 1.2 times 10 to the minus 5 minus 3 times 1.9 10 to the minus 5 equals, we'll want to 1 on x times 0.05 equals, and we get minus 238.8 degrees. Okay, so that's what I get for the change in temperature. So if I add that to the initial temperature as 250, I get 11.22. I think I've done something wrong, but it's close to 13, which will do. Okay, next question. A quantity of an ideal gas at 10 degrees Celsius and 100 kilopascals occupies a volume of 2.5 cubic meters. A process results in the pressure being raised to 300 kilopascals and the volume decreased to 1.29 cubic meters. The temperature of the gas is now closest to. So this is a PV equals nRT type problem. And so P1 is equal to 100 kilopascals. T1 is equal to 10 degrees C, which for the purpose of this should be converted to 283 Kelvin. And V1 equals 2.50 meters cubed. And P2 is 300 kilopascals, T2 equals don't know, and V2 is equal to 1.29 cubic meters. So given that PV over T is constant, we can say P1 V1 over T1 is equal to P2 V2 over T2. So therefore T2 is equal to P2 V2 over P1 V1 times T1, and so we can say it is 300, and the kilopascals doesn't matter because we've got them on the top and the bottom. So 300 times 1.29 divide brackets 100 times 2.5 equals times the original temperature, which is 283, equals 438, and we want it in degrees Celsius, so we're going to take away 273, and we get, no, not divide, times, take 273 equals, and we get 165 degrees. So that's that one. Okay. Two samples of a liquid with unknown specific heat are mixed together in an insulated vessel. One sample has a mass of 0.5 kilograms and starts with a temperature of 8 degrees Celsius. The second sample starts with a temperature of 60 degrees. When equilibrium is established, the final temperature of the mix is 40 degrees. The mass of the second sample was closest to what? Okay, All right. Well, Q lost by 1 must be equal to Q gained by the other. So if we call the specific heat C, then we have 0.5 kilograms M times C times delta T, which is 60 minus 8. This must be equal to the mass of the other sample times, oh, it's not 60, it's 40. Okay, the final temperature is 40. Must be equal to the mass of the other sample times C times 60 minus 40. Okay, C's cancel, and so we get M is equal to 0.5 times 40 minus 8 over 60 minus 40 equals, okay, 0.5 times brackets 40 minus 8 equals divide brackets 60 divide minus 40 equals 0.8 kilograms. So 0.8 kilograms it is.